Hello, my name is OSub Kwon, and I'm going to talk about my job market paper on strategic experimentation. To clarify what I mean by strategic experimentation, I would like to first point out that most first-hand information in the world is generated by risky experimentation. For example, if a doctor wants to know whether a medicine can cure COVID-19, he must try it out on the patients to learn about it. On one hand, in the short run, this experimentation is risky because the medicine may be ineffective or may even be harmful to the patient. On the other hand, in the long run, once the doctor learns about whether the medicine is effective, he will know about it forever and he will know better what to do in the future. Therefore, the main problem of experimentation is to decide how much short-run risk to bear in order to generate information that will benefit you in the long run. Now, if there is information spillover, that is to say, if I can learn from others without doing my own experimentation, then you can imagine that there will be some free riding, so experimentation starts to be strategic, and the problem becomes a public good game. However, this public good game has two features that make it very, very special. The first special feature is that this public good game is mainly about beliefs. What do I mean by that? If a medicine is believed to be effective with 95% chance, very promising, then every doctor will experiment with it voluntarily. In this case, there is no conflict between the social and private interest. However, if the medicine is believed to be effective with 50% chance, not so promising, then the doctors may not want to experiment with it, but the society may still want to give it a shot. The reason why this happens is precisely because the doctors do not fully internalize the social value of information, and therefore they are willing to take less risk than what the society wants. So the problem is mainly about belief. It is that the society wants to take more short-run risk and experiment at a lower belief than the individuals. The second special feature is that this public good game is repeated, but the end point is endogenously determined. What do I mean by that? You can imagine that the experimentation of a medicine takes time, maybe several months, and the information spillover occurs as experimentation goes on. So this situation is a dynamic game, it is a repeated game, but the very interesting thing is that the experimentation cannot go on forever. As people experiment with the medicine, there must be a point at which the type of the medicine is revealed. Starting from that point, there can be no meaningful interaction among the players. So the game essentially ends when the state is revealed, but the number of periods is not exogenously given, it is endogenously determined by the actions of the players and how the experimentation unfolds. So two features I want to emphasize throughout the whole presentation. This public good game is mainly about belief, it is repeated. This public good game is about belief, it is repeated. So in this paper, I want to learn about this repeated public good game. More specifically, what I want to do is to test a version of an econometrical model, which I actually changed quite a lot. I have two research questions in mind. The first research question is, because this game is about belief, do people take more short-run risk if it benefits others in the long run? The answer will be partially yes. The second research question is, because this is a repeated game, is there any reciprocation among the players in this repeated game? We know that even in the finitely repeated person's dilemma, there is some reciprocation. Something like, if you defect, then I'll defect more. We want to know whether there is also this kind of reciprocation in this environment. The answer will be quite surprisingly no. Now, this econometrical model is quite important in the theoretical literature, but didn't get much attention from the experimental literature. Why? It's because this model is hard to implement in the lab. This game is about belief, it is repeated, and yet we know that people are base irrational. People generally cannot calculate posterior properly. So what I'm going to show you is an experimental design with a learning process where I make the posterior calculation very, very easy. I do this because I know people are base irrational, but I don't care. I want to focus on the public good aspect of the problem. I claim that my design is going to get base irrationality out of my way. So here is the overview of the experiment. The experiment has 3 parts. I'm not going to talk about part 1, and I'm going to mainly describe part 3 because part 2 is just a one-player version of part 3. So once I tell you how part 3 works, you'll also know how part 2 works. So let me start to describe part 3. As I told you, this is a repeated game. The continuation probability delta is 7 out of 8, and I only pay the last period of the super game. So up to this point, everything is quite standard as a repeated game. But before everything starts, nature chooses a ball from a box with 50 black balls and 100 white balls. So 1/3 prior belief that this chosen ball is black. The color of this chosen ball is the common state that every player wants to learn. It does not change throughout the whole super game. After the game starts, in every period, each of n player chooses between a risky arm and a safe arm. So binary choice in every period, risky or safe. The risky arm will give you a payoff that depends on the state, which is the color of the chosen ball, and the safe arm will give you a payoff that does not depend on the color of the chosen ball. Now, nothing interesting will happen to the safe arm, so let's talk more about the risky arm. After the players make their choices, nature will permanently remove L black balls from the box for every player choosing the risky arm. That is to say, if no player chooses the risky arm, then no black balls will be removed. But if one player chooses the risky arm, then L black balls will be removed. And if 2 players chooses the risky arm, then 2 L black balls will be removed, and so on. 2 things I want to emphasize here. Nature will only remove the black balls, and the white balls will never be removed. And second, the removal is permanent, so that the black balls removed today will never appear in the box in the future. After the balls are removed, nature announces whether the chosen ball is removed. Basically, it will tell everybody whether the chosen ball is here or here. So to summarize, in a period, 3 things happens. A player chooses between the risky arm and the safe arm. Nature removes the ball according to how player choose, and then nature announces whether the chosen ball is here or here. So to understand what is going on here, let me first establish the following claim. I claim that the more black balls are removed, the more informed the players are about the color of the chosen ball. Why? Let's say 10 black balls are removed. Then either the chosen ball is removed or not removed. If it is removed, then you know that the chosen ball can only be black. But if the chosen ball is not removed, then the posterior will become something lower than 1/3. In this case, it is 40 over 140, which is simply the fraction of the remaining black balls in the box. So after 10 black balls are removed, your posterior becomes either 1 or 40 over 140, which is the mean preserving spread of the prior belief, 1/3. This means you became more informed. To the extreme, if all 50 black balls are removed, then knowing whether the chosen ball is removed or not removed automatically tells you about the state. So the takeaway here is that the more black balls are removed, the more informed the players are about the color of the chosen ball. What immediately follows is that the removal of the black balls is information generation. That is, if you choose a risky arm, then you are learning more about the state of the world. Note, the posterior is simply the fraction of the remaining black balls in the box. so you don't need Bayes' formula to calculate posterior. Because of this design, we can focus more on the strategic element of the game without worrying too much about Bayes' irrationality. And because the number of remaining black balls is directly linked to a posterior probability, from now on, when I say believe, I will always refer to the number of remaining black balls in the box and not the posterior probability per se. Finally, let's look at the payoff. If you choose the risky arm, then you'll get $16 if the chosen ball is black and nothing otherwise. If you choose a safe arm, you'll get $15 with 1/3 chance. So from ex ante point of view, the lottery of the risky arm stochastically dominates the lottery of the safe arm. However, after some black balls are removed, either you know that the chosen ball is removed, in which case the state is forever revealed and your decision becomes trivial, or the chosen ball is not removed, in which case, as more and more black balls get removed, you become more and more pessimistic about the state of the world, and choosing the risky arm becomes more and more risky relative to the safe arm. At some point, you will realize the risk outweighs the value of new information generated by the risky arm. At some cutoff, you want to stop choosing the risky arm, and that cutoff is what we are interested in, because that cutoff is where you stop learning about the state of the world, and that cutoff is basically determines how much information the society ends up with. And because we are interested in that cutoff and not too much interested in what happens when the chosen ball is removed, I always use a strategy method to ask the subjects, what are you going to do if the chosen ball is removed? What are you going to do if the chosen ball is not removed? Now, what does the theory says about the cutoff? Instead of the whole theory, I will give you some magic numbers. The socially efficient cutoff has this simple expression. I want to remind you that this is the number of remaining black balls in the box, not the probability. K bar 0, the first term, is the myopic cutoff. It is the cutoff where the period payoff of the risky arm is equal to the period payoff of the safe arm on average. This is where you're indifferent between the two lotteries if you're risk neutral. However, precisely because choosing the risky arm will give you information that will benefit you in the future, you should go beyond the myopic cutoff by this much. I would like to remind you that delta is the continuation probability, n is the number of players, L is the number of black balls removed per choice of risky arm, which I interpret as the speed of learning. Now, because everything else except n and L is held constant, so the efficient cutoff is determined by the product NL. What is NL? It is the number of black balls that you can remove if all the players choose the risky arm. So this is the social speed of learning. And the intuition behind this expression is that the higher the social speed of learning, the higher the social value of information, which will justify experimentation at lower belief. So the higher NL, the lower the efficient cutoff. Given this expression, I can also define what I call the selfish cutoff, which is simply the special case when n is equal to 1. This is the optimal cutoff when you experiment alone. This cutoff is where you should stop experimenting if you only consider your private value of information. So naturally, the selfish cutoff is higher than the efficient cutoff. This relates back to what I talked about the doctors in the introduction. 50% may be below the selfish cutoff, so that the doctors may want to stop experimenting, but it may be above the efficient cutoff, so that the society may still want to give it a shot. The very interesting equilibrium prediction is that regardless of n, the equilibrium cutoff is the selfish cutoff and never below, which means that the players will always quit experimenting at a higher belief than what the society wants, and the society will end up with inefficient amount of information. Now recall that this is an infinitely repeated game, but the Folk theorem fails. so that the players cannot achieve efficiency even in the best equilibrium. This also relates back to what I talked about in the introduction. The experimentation cannot go on forever. At some point, the state is revealed, and the game will unravel from that point. So given the theoretical results, now here are the treatments. I mainly play with the speed of learning L and the number of players N. Treatment 1 and treatment 2 are only different in N. So by comparing these two treatments, we can test the main equilibrium prediction that says N does not affect the amount of information generated. Then why do I introduce treatment 3? Treatment 2 and treatment 3 has the same social speed of learning, which is 6. So they have the same efficient cutoff. So by comparing these two treatments, we can see whether larger group tends to be more or less efficient than the smaller groups. So now the results, I mainly look at the median cutoff in the super games that have appeared more than 10 peers. The reason that I look at the long super games is that those short super games end before anybody reaches any cutoff, so those are not interesting. Remember that part 2 is a one-player version of part 3. It is a special case where n is equal to 1. Here I want to know if they experiment alone, at what cutoff value people will stop. What I find is that very, very surprisingly, the median cutoff, the actual data, is very, very close to the theoretical prediction of the selfish cutoff. And you can also see that the comparative static is correct. Treatment 3 has a higher L, so they can learn faster in treatment 3, and they indeed go to a lower belief. So although this is a very new environment, it seems that people know what they're doing. Now let's look at our main part 3. Two things suggest that our theoretical predictions is not true. First, equilibrium says that people should stop at the same belief in part 2 and in part 3. But we can see that in every treatment, people stop at the lower belief in part 3 than in part 2. Second, if we compare treatment 1 and treatment 2, again, equilibrium predicts that people should stop at the same belief in treatment 1 and treatment 2. But we can see that in treatment 2, with more people, they stop at a lower belief. So this seems to suggest that the more players there are, the lower belief people tend to go, which is against the equilibrium prediction. However, that doesn't mean people are getting anywhere close to efficiency. In all treatments, efficiency requires people to stop at a very low belief, but people will stop much higher. By the way, we can see that the larger groups tend to be slightly less efficient than the smaller groups. Why? Because treatment 2 and treatment 3 has the same socially efficient cutoff, but treatment 2 stop at a slightly above belief than treatment 3. But this is a relatively weak result. But to summarize the main point, we see that the more players give the lower stopping belief. So if a player experiments with other players, she tends to go lower than her selfish cutoff. This is against the equilibrium prediction. Equilibrium says that the stopping belief has nothing to do with the number of players. Now, you might not find this result surprising because we know that even in the finitely repeated presence dilemma, there is some cooperation. But then in finitely repeated presence dilemma, the cooperation is sustained by reciprocation, something like if you defect, I'll defect more. If you cooperate, I will cooperate more. The next question is, does this game also have this kind of reciprocation? To answer that, I use the strategy method to ask the subject, if the other players previously chose a risky arm, what are you going to do? If the other players previously chose the safe arm, what are you going to do? Basically, I allow them to react to what other players have done in the previous period. Then I ran a probability regression of the dummy variable about whether you choose the risky arm, on the belief, and on whether the other player previously chose the risky arm. What I find is that, yes, people react to the level of belief, highly significant, But no, very surprisingly, whatever the other players previously did, they do almost the same thing. The difference is not statistically significant, marginally significant here, but the direction is opposite. This can also be seen graphically. This is a graph of treatment 1. At every level of belief, the blue line indicates how frequently you are going to choose the risky arm if the other player previously chose a safe arm, and the red line indicates how frequently you're going to choose a risky arm if the other player previously chose the risky arm. I find that at every level of belief, they do almost exactly the same thing, whatever the other player previously did. And this applies to all treatments. Everything is similar here in treatment 2. Everything is similar here in treatment 3. So my second result is that there is no evidence for reciprocation, and the players react only to the belief and not too much to other players' past action. So to summarize, this paper studies how people experiment with risky options when there is information spillover. I find that in contrast to the equilibrium prediction, more players give lower stopping belief. So there is some altruistic risk-taking. However, surprisingly, this is a repeated game, but I find no evidence for reciprocation. So they do not reciprocate this kind of altruistic risk-taking. My conjecture for why this is happening is because the intention is very difficult to read. So for example, if you see me experimenting with a risky arm, you don't know whether I'm doing this out of kindness because I want to help you, or simply because I value information. And because of that, you are not likely to reciprocate me by also doing the experimentation. Let's not forget about the methodological contribution. I designed a dynamic learning process that makes posterior calculation very easy at every point of the game. This design allows us to study the public good problem without worrying about base irrationality getting in the way. Finally, let's talk about how this paper is related to one past paper. There are several lines of relevant research, but I just want to talk about one paper. In a recent paper, Johannes Hörner and his co-authors say that for a broad class of learning processes, the players can achieve efficiency in equilibrium by reciprocation. However, in this paper, I find that subjects do not reciprocate even when given a lot of chances. So even if we use a learning process that they say will work, I doubt that people will actually reach efficiency. This, I believe, is important because in many environments, we rely on the folk theorem to help us solve inefficiency. Yet I found that in this quite important environment, reciprocation doesn't work. Thank you for your attention. This video is available on my personal website. Thank you.